Testing large integers for primality creates a severe bottleneck in cryptography. Standard tests rely on arbitrary precision modular arithmetic. This is a computational method that forces processors to divide numbers so massive they exceed the hardware's native memory registers. Traditional algorithms process enormous datasets by repeating expensive division operations millions of times. This sheer volume puts immense strain on processor clock cycles. The Zarkouna method, or index exclusion method, provides an alternative. It is a deterministic primality test, an algorithm that guarantees a number is prime or composite with absolute mathematical certainty that circumvents these heavy modulo operations entirely. Instead of repeatedly dividing the large integer, n, the algorithm projects it into an absolute space. This is a mathematical matrix natively structured to exclude any numbers that are trivial multiples of 2 or 3. By removing these trivial multiples, the algorithm replaces heavy modular division with basic algebraic detection. It relies entirely on floor functions, which round numbers down to the nearest integer, and bitwise shifts, which are extremely fast operations moving binary data left or right within a processor. Because the method uses these native processor instructions to track a single coordinate, it operates with O1 spatial memory complexity. This is a computer science classification, meaning the amount of memory the algorithm requires remains constant, regardless of how massive the integer n becomes. By abandoning the massive magnitude of the original number and relying strictly on native processor logic, this method bypasses the standard clock cycle limits of high-performance cryptographic computing. The process begins with a simple purge. If the integer n is cleanly divisible by 2 or 3, it is immediately rejected as composite. This animated diagram shows the mathematical engine of the absolute space. This equation is a bijective generating function, meaning it creates a perfect one-to-one mapping between values, and it uses a parity oscillator, a mathematical switch that flips between two states based on whether n is even or odd. Next, we extract the integer's spatial polarity, represented by the variable a. This is calculated as n modulo 3, which isolates the remainder after dividing by 3. We plug that polarity into a simple subtraction and division formula to deduce the target spatial coordinate, labeled n target. Normally, primality algorithms require computing the square root of the massive original integer. The Zarkouna method calculates a bounding limit without touching that original number again. Instead, it calculates the spatial horizon, r_lim, by applying a square root solely to a fraction of the newly found spatial coordinate. Once the target coordinate and the spatial horizon are established, the algorithm permanently erases the original magnitude n from its memory. The search for primality is no longer a question of massive integer factoring. It is strictly about determining if this specific spatial coordinate can survive a topological sweep. To test the coordinate survival, the algorithm deploys an arsenal of prime engines, denoted as p. These engines correspond to the numbers generated by indices up to the spatial horizon limit. This animated diagram shows the algebraic target estimator. It takes a specific prime engine and calculates the approximate entry index required to land near the target coordinate. This estimator allows the algorithm to target the exact vicinity of the coordinate in constant time, skipping the entire sequence of numbers leading up to it. Once targeted, the algorithm fires its second operator, the exclusion equation, or case of p of n. Kp is a closed-form equation, meaning it can be evaluated in a finite, predictable number of standard operations. It acts as a mathematical stepping function that strictly generates surviving indices, the locations that are not multiples of the prime engine. If the step lands directly on the target coordinate, the coordinate survives. But if the equation calculates position x minus 1, and its next step lands on x plus 1, it has leaped completely over the target. This overstep is called a spatial fracture. An overstep proves the coordinate is an exclusion zone. Checking for primality is now just a matter of checking for this geometric discontinuity. Let's run a composite integer through the trace. N equals 779, which easily passes the initial checks, since it is not divisible by 2 or 3. This execution trace displays the target projection. 779 yields a polarity of 2, which gives us a target spatial index of 259. The horizon limit calculates out to 9. Based on that horizon limit, the prime engines we need to evaluate are 7, 11, 13, 17, 19, and 23. The algorithm fires the algebraic target estimator and evaluating the jump equation for the first 4 prime engines. For engines 7, 11, 13, and 17, the KP equation generates exactly index 259. The coordinate survives the initial sweeps. The trace then arrives at prime engine 19. At step 244, the jump equation lands on coordinate 258. On the very next iteration, step 245, it immediately outputs 260. Coordinate 259 has been cleanly bypassed. The space is confirmed as a topological void. This fracture triggers an instantaneous halt. The integer 779 is declared composite, and the factor 19 is identified, all without executing a single division operation against the original magnitude. Now we map the algorithm's behavior when challenged by a prime magnitude, n equals 601. This trace table shows the new projection variables. The polarity is 1. The spatial index is 200, and the limit index is 8. The ballistic sieving begins again, deploying prime engines 7 through 23 to sweep the space up to the horizon limit. The algebraic target estimator brackets the target area 6 consecutive times. At every single iteration across the entire arsenal of engines, the jump equation generates coordinate 200 precisely. The coordinate withstood the entirety of the exclusion waves. Because no geometric overstep occurred before the algorithm reached its spatial horizon, the number 601 is mathematically certified as an absolute prime. These 2 execution traces demonstrate the total computational autonomy of the index theory approach. This split screen compares the hardware load. On the left, an arithmetic logic unit, the specific part of a CPU that performs math operations, is weighed down by traditional big-end modulo divisions. On the right, the processor executes the highly localized floor function logic of the k-subsys jump equations. Because the algorithm drops the massive integer n entirely and zeroes in on a single spatial coordinate, the required memory overhead stays perfectly flat at O of 1. The processor stops calculating arbitrary precision arithmetic. It only executes rapid additions and bitwise shifts at the hardware level. Operating exclusively with these lightweight native instructions pushes the required hardware clock cycles down to their absolute theoretical baseline. The Zarkouna method offers a deterministically true algorithm that serves as a highly optimized blueprint for modern high-performance computing. By treating primality not as a problem of division, but as a topography of exclusion zones, this algorithm actively removes the mathematical drag that constrains cryptographic hardware.